All right, good afternoon, everybody. My name is Josiah Gaskin. I work as a software engineer at Facebook, and I work on our internal Android developer tools team. In case a few more people are still trickling in, let's continue the poll of the room that I did. Think back and find the worst Android build that you ever had to sit through, where you went and got a cup of coffee and you came back and it was still running. How long was that? Was it, say, longer than a minute? Longer than 5? 10? 15? 20? 25? 30? Okay, there's still a few hands up. So build time on Android has always been a little bit of a hot issue. Today I'd like to talk to you about our build system, Buck, that we built to try and solve that, among other problems. So my team, the internal developer tools team, is focused on our engineers, our production engineers, and we want them to be as efficient as possible. And we want their workflow to be as pleasant as possible. And so we build a bunch of tools to help them do that, but we also want to make sure that we're giving back to the community, we're giving back to you. And so whenever possible, we take these tools and we open source them. And so like some of these other tools, Buck is open source. It's available on our GitHub. And buckbuild.com is our documentation site. So some of you I already know are using Buck. Thank you. Awesome. And maybe if you haven't ever given it a try, what I'm going to talk to you about today is going to maybe prompt you to do so. So let's start by talking about our workflow. This is what we do every day. And we edit some code. And as we're working on our app, maybe we're trying to tweak some UI, fix a bug, iterate on a new feature. We then go to compile the code. We install on our device or our emulator. And we relaunch the app. And then we navigate or we reset state somehow. We go back to where the bug was found or back to the feature, the screen implementing our feature, and we test to see whether our code change did what we wanted it to. And if it did, fantastic, we're done. But if it, more often than not, it didn't. And development is a very iterative process. And so most of the time, we go back to the top. And this is the workflow that I care about. And this is the workflow that I'm trying to optimize for my developers and, by extension, all of you who also use our tools. So let's take a look at what that actually looks like. I've got this demo app here, and it's this master detail controller. And I've got an email, and the from address is displaying at the bottom. And I'd really like to move it to the top. So here I've identified the code necessary to change. And I'm going to tell Buck to build and run this app. And here I've disabled all the incrementality that Buck knows about. And we're going to do a full build from scratch. So first, Buck is going to figure out what files belong to my project, what the state of the world is. It's going to do some compilation. And already we're helped a little bit by the fact that all of this runs in parallel. I didn't disable parallel build because we're going to be here all day. But then we compile an APK, we install it, and now we relaunch the app. And we go back to the screen that we were looking at before. We reset state. And we verify that our change worked. It did what we wanted. And here we're lucky, because if it hadn't, we would have had to go back to the top. And obviously, this is like a really contrived example. But this small demo app represents a slice of our everyday workflows that is probably somewhat representative of what you and I go through every day. And when we break that down by the amount of time that we spent in each of these steps, we can see that it adds up to quite a bit. For this small demo app, this is 42 seconds just to do this tiny little tweak. It wasn't really a major thing. It was just rearranging some lines, and we didn't change any public APIs, just this one method body. And this is frustrating, because we recompiled the whole app. I didn't change the whole app. I tweaked one line. I tweaked one method body. And so this is where the notion of incrementality comes from. That idea that the size of the work done by the build system and the size of the time that you have to wait should be proportional to the size of the change that you've made. And a lot of frustration stems from when these two are not equal or not proportional, when, as you saw, the size of the work done is larger than the size of the change that I made. And so this is our guiding principle in Buck, that everything should be as incremental as possible. So I'm going to start by talking about how Buck today already makes portions of this workflow incremental, and how pretty soon we're going to see more and more of this workflow become incremental. So let's start with the biggest chunk of time here, compilation. And Buck's notion of incremental compilation is based around a rule. So this is a definition of a Buck rule. It's an Android library, it has a name, it has dependencies on some other rules, and it has a glob of sources, so all the Java files in this directory. And these dependencies together form a rule tree. So this is our dependency graph, or our rule tree. And when we do a full build, we build every single node in this tree, and we build from the ground up. So we first build out all the leaves. Once those are built, we can go and build the things that depend on them. And then finally, at the top, we can rebuild the actual node that we wanted. In an incremental build, though, Buck calculates the minimal set of changes that need to be recompiled based on the changes that you're making to the code. So let's say we change node F. We change one of its files, and we change a public API. That means F obviously needs to be rebuilt. And since its public API has changed, C, which has a dependency on F, also needs to be rebuilt. It consumes those public APIs. One of its inputs has changed. But G has no dependency there, and so we leave it alone. We reuse the artifact from our previous build. In the same fashion, the rest of our build graph, the other half, also has not changed. There's no dependencies from anything over on this side to our changed code, so we can leave it alone. We can reuse, again, those same artifacts. OK, and now here's one of the first major optimizations we made to Buck. C has rebuilt. And so technically, one of the inputs to A has changed. But C's public API has not changed. Remember, it was just rebuilt because one of the APIs that it consumes had an edit made to it. And so C still exposes the same interface. And so that means that A's dependency on C does not invalidate A. We can still reuse the same artifact for A because we consume only public APIs and we haven't changed any of those. So these are the this is how Buck calculates that minimal set of things that need to be changed, and we're working on further improvements here. For example, we're working on making sure that we can start compilation on C before F has even been built. Remember, I talked about how the tree is rebuilt from the ground up. And so we expect a blog post on that very, very shortly. It should just change under the hood. If you're using Buck, all you have to do is flip a flag, and then you should see much better parallelization in your incremental builds. Next up, let's look at the next step in the workflow, and that's installation. So in a stock install, you compile your code, and it produces this classes.dex file. And that gets packaged into an APK. But it's not the only thing that goes into the APK. As we all know, your resources, your native libs, your assets, all the other bits and pieces of your app also get packaged into this APK. And so when we push it over to the device or to the emulator, we pay to push all of those bytes over ADB, even if the only thing that has changed between the last build and the current one is our code. So Buck's solution to this is incremental install, which we call exopackage. And the way that it works is we split up your code into multiple dex files. So there's still a primary dex file, the classes.dex, that goes into the APK. But Buck puts the minimum number of classes in there possible so that your app barely boots. Once it boots, it loads the secondary dex files from a different location. So now we can push the APK over to the device. And this happens a little bit faster because the APK is smaller. And the secondary dex files go into a different directory, a temp directory, owned by the app. So that's our first build. But once that's in place, we can leave the APK alone. And when we do an incremental build, and create a new secondary DEX file that we want to push over to the device, we can just push it to that temporary directory. And here we've left the APK alone. We haven't paid for anything that hasn't changed. We've only paid for the one block of code that has changed, and we pushed that over to the device. Additionally, we haven't had to reinstall the APK. We didn't need to invoke the package manager to remove the old one and bring in a new one. Here I'm specifically focusing on code, but we also have support for resource and native lib changes in exopackage. And so whatever type of change that you're doing, you only pay for the one thing that you have changed to be pushed over to the device, and you can skip the rest of it. Excellent. So this is the state of Buck today. And let's see what happens when we turn all of those features on and rerun that demo scenario. So once again, I'm going to make that same change. And here, I'm going to tell Buck to build and install my app again. And Buck is going to calculate which modules have changed and rebuild the, oh, it's already done. So Buck has reinstalled just the one module that has changed. And now, I also care that my build is correct, that I haven't used a stale artifact. And so I'm going to go back, and I'm going to check and see that, in fact, oh good, my change did in fact make it into the app. And when we look at our time saved here, this is pretty great. We're down to just 20 seconds for this change end to end, and that's a 53% reduction over the last time I ran this. And what I love about this statistic is as your app gets bigger and more complex, this reduction only gets bigger because the time for an incremental build stays relatively constant by definition. If your work done is proportional to the change that you're making, and you keep making those small changes, it's going to take a small amount of time. But the time for a full build increases and increases as the size and complexity of your app increases. And so I can assure you that we're seeing way better than a 53% win for an incremental build versus a full build. So what's next? Well, we're starting to eye the time spent in that second half of this workflow cycle. So why does this happen? Why did we spend that time relaunching the app and resetting the state? Why did we have to navigate? And the answer lies in the fact that we've changed code. So in this example, I edited the code. I changed the definition of the bytecode that lives in a class file. So I have to kill the app in order to load that changed code definition and see its effect in the app. And that meant that I'm cold starting the app, and that meant my state is gone. I have to reset it either via a code path or, as you saw in this little demo, manually. But what if I didn't have to do that? What if instead I could just load the code into the app, don't kill the app, and then my state is already there and set to go? And I can see you probably already know what I'm talking about, and this is the definition of hot swapping. That is reloading code in the app while the app is still running, so without performing that cold reboot. Instant Run is a pretty good example of this. This is an idea that's been around for a while. But as we looked at the existing implementations, we weren't really satisfied with anything that was out there, and so we tried a bunch of them. And we realized we wanted more. We wanted more correctness, and we wanted more flexibility. We wanted to be able to define new classes or change method names, method signatures, add or remove fields, that kind of thing. And we wanted more correctness. We wanted more control over what gets reset in the app when the new code definition gets loaded in. And so that's why we're bringing hot swap to Buck, and we're building our own approach. So let's dive in and talk a little bit about how it works. So as many of you know, the thing in Java responsible for loading classes into memory and making them executable is the class loader. So in your app, again, this is that structure that I showed, you usually have two class loaders. You have an app class loader that loads classes from your classes.dex file, and you have a system class loader that provides you access to the Android system classes, stuff like the view or the application. And class loaders form a hierarchy, so if I don't find what I want in my class loader, I can just go and ask my parent and say, hey, do you have this class definition? And so this is the hierarchy that exists by default. So the way we enable hot swapping is we write our own class loader. This is the exopackage class loader, and it's responsible for loading code from those secondary DEX files. And when we want to hot swap, all we have to do is take our recompiled code, push it into that temporary directory again, and then notify that exopackage class loader that new code is available, and it should refresh its definition of the world. And now, when we go to load code, we ask this exopackage class loader, hey, please give me this class definition. It provides the new definition, and the system can continue from there. So here's that same demo again. And I'm going to make that same exact change, but this time, we're going to instruct Buck by passing an extra command line flag that we want to do a hot swap instead of an app restart. So I've made the same exact change. I pass an extra flag, and now Buck does that same incremental build and install, and I can see my activity has refreshed on the right, and we're already done. We can see the change that we've made. All of the state that's been necessary to reset has been reset, and this took a fraction of the time that it took before. So here, that 17 seconds has been, again, greatly reduced. And we're down to just 5 seconds for this change end to end. And what I love about this is it's a virtuous cycle. The more often that you do this cycle, and the faster that we can make it, the better off you are, the better your development experience is. Because if it takes minutes or hours, I don't know, to see your change in the app, you're going to push off running your code. You're going to write more code before you go and you verify. And we do a lot of things to try and mitigate that pain today. We write little demo apps and iterate quickly in the demo app before merging the feature back to the main app. Or we write unit tests so that we can test on the desktop JVM rather than pushing to the emulator or device. And these aren't necessarily bad. But when you really want to go into the app and see your change live in the app with the full production stack, there's really no substitute for that, and so we want to make this cycle as fast as possible. So this is an 88% reduction from that non-incremental all the way to this tiny little refresh. Let's talk about how you turn it on, and then I'm going to talk about the ways that we've implemented it and some of the gotchas that we had to face. So the way you enable it is you add a new exopackage mode. So remember, exopackage was that incremental install that I talked about. And you flip this on by turning on exopackage modes, and you add modules. And you'll see why in a second, because the implementation that I'm talking about relies on modularizing your app. And next, you change the way that you invoke these modules. So modularizing your code usually means pulling out explicit references and replacing them with dynamic lookups. So here, I've taken the typical code for creating an intent or instantiating a fragment, and now I'm doing it dynamically rather than baking in that reference at compile time. Doing this dynamically means that we get a fresh version of the class every time by going back to the class loader and saying, hey, give me the definition of this class. That way the class loader can say, oh, I have a new definition for the class. Let me give it to you. It also allows us to break up these individual classes into multiple DEX files, which will be important. This is kind of awkward, though, because now you're stuck with reflection. The Fragment API in particular has a method which you may be tempted to use, but I'm going to tell you not to, because this method actually caches internally. It's got an internal memoization optimization that's going to completely destroy our ability to hot swap. So we've defined some helper methods for you that take care of all of this and do the right thing by always asking for a new definition. So we have one to create an intent and one to create a new fragment. The next thing that you have to do is react to the fact that there is new code loaded into your app. And we all construct our apps a little bit differently. And so the state that needs to be refreshed is also going to be a little bit different. So in my demo app, you saw that I refreshed the top activity. I restarted the top activity. That might not always be what you want to do. So rather than try and intuit what it is you want, we let you control what gets refreshed on a code change. So right now, there's a simple callback that you can register, and you can see whenever code changes via hot loading. And then we let you respond. And so you can do whatever you want, obviously, in this callback, but we've provided some helper functions to allow you to restart the top activity, refresh a given fragment if your app is fragment-based, or go nuclear and restart the whole app, and this will perform a cold start. So in the demo app, this is the code that powered that hot swap refresh. So I register this listener, this callback, and then I pass it the current activity instance, and we recreate that current activity instance and repass the same intent that was used to originally create the activity. So hopefully all of the state that you used to initially invoke the activity will just come back for you. And then, since I'm only hot swapping in this particular demo, I'm only hot swapping this one activity, I can just add this callback in my onResume and remove it again in my onPause. Realistically, though, you probably want to be able to hot swap more than just this one activity, and you definitely don't want this boilerplate in every activity you're working on. So one option is to register an activity lifecycle callback. Then you can save a reference to whatever activity is on top. And when new code comes in, you just refresh that top activity. If you're using a framework, you probably want framework level support, so like a view management framework. If you maintain that, I would love to talk to you about how we can support you in adding support for this to your view management framework. And then if you construct your app via fragments, you can use our fragment helper to refresh a given instance of a fragment. So we'll go to the fragment, find its manager, remove the old fragment, instantiate a new one from the new class definition, and pass it all the same args bundle that was used to construct the fragment initially, as well as restoring any saved instance state. So sort of similar to what happens when you reorient your phone, but we do it all for you under the hood. But again, like these are just helper functions. We'd love to write more of them if you come to us with specific use cases. But you can also do whatever it is you want here. And you can register lots of these callbacks. You're not obviously limited to just one. So you can respond at any level in your app, maybe even in like a background service or something like that. So that's what hot swap is and how you use it. And I want to get into a little bit of the other side of things. So I've talked about the speed, and I've talked about and I've hinted at some of the flexibility, but I want to talk about correctness for a minute, because that's really what killed us when we tried to investigate some of these other instant run type solutions. And so the first thing I want to talk about is sort of an implementation detail, but I ran into this when I was first trying to build this system, and that's class loader caching. So maybe you caught this on the earlier slides, but I kind of glossed over the fact that all class loaders have this optimization in them, where when you ask it for a class definition, the very first thing it does is it looks in a cache and says, have I already loaded that class into memory? If so, I'll just return that. And only if we don't find it in the cache do we go to the dex file on disk. And the first time we go to the dex file on disk and we load, or the odex file if it's been optimized, the first time we go there, we take the parsed representation and we save that in the cache. And so all subsequent requests are served by that cache, even if we've changed the definition on disk. We really like this cache. We would really like to not bypass it. And so ideally, we would be able to take the classes that we've changed and remove them from this cache. But it's all implemented in the native layer. There are 0 APIs to interact with it. And so any access that we do to it would be by nature unsafe. So we do the next best thing. And that's we throw away the class loader entirely, and that gets rid of its cache. So what happens is we create this like sacrificial delegate that loads our dex files. And then whenever we have a new dex file, we throw away the delegate, we install the new dex file, and we create a new delegate. And it takes a little bit to warm up, but as soon as it finishes warming up, it's going to be just as fast as the old one. And we can take advantage of this optimization most of the time, but it still allows us to hot swap when we want. The other gotcha that I want to talk about is inconsistent state. So here's one example. I have some global state, and I'm sorry it's a little hard to read, but I have this foo.class, which is a singleton pattern. So I have a static instance, and I have a getInstance function, which just returns the static instance or creates a new one if none exists. And it has one piece of state on it, this username field. And I'm going to walk through an example here where I access this singleton. And I want to make clear that this is all in a single thread. There's no funny like multi-threading race condition going on. None of that. This is all happening on a single thread. But I get into this weird inconsistent state where I set the username in class A, and then a few seconds later in class B, I try to check some property of that state, and I get this null pointer exception. Somehow username is null, even though I've just set it a few seconds before. And it gets weirder because I can assert that the username is equal to the value that I set previously. But at the same time, in b.class, I can assert that it is in fact null. So what's going on here? How can this like little piece of Heisenberg state be both null and have the value that I expect? And the answer is A and B are pointing to entirely different versions of foo.class. So when you have a static field, the reference to that field is stored in the class definition, in the in-memory representation of that class. And here I've hot swapped foo.class, presumably. So I have two instances in memory, and A is pointing to one, B is pointing to the other. I get this inconsistent state where my assumptions that I make from one are no longer going to hold true in the other. So how do we fix this? Well, we fix this by making sure that hot swapping is somewhat of an atomic operation, that as you hot swap code, all the classes that hold strong references to that piece of code that you are changing also come along with it. And the easiest way to do that is to bundle your app into modules, into individual chunks of code where you have strong references in between classes in that chunk, but all incoming references to that code are dynamic lookups. So let's take a look at what that looks like, sort of conceptually, and then we'll talk about how Buck enables you to do this. So conceptually, we first want to make sure that the edges in between our code are these dynamic lookups that I talked about earlier. Then I want to tell Buck, hey, I have these roots. So in this example, I have activity 1 and activity 2, and I want to be able to hot swap each of these individually. I want them to each be their own module. They share a dependency on this fragment, and so when I go to walk the graph, I mark each of the roots as belonging to their own module, and then I walk all the nodes that are reachable and say, hey, what module do you belong to? In this case, both activity 1 and 2 depend on the fragment. They reference it, and so I will put my fragment into its own module and then mark a dependency between the modules of activity 1, activity 2, and the fragment. And so now when Buck goes to build your code and organize it into multiple dex files, this is the result. All of the other like app state goes into other classes.dex files, and our modular dexes, we get one for activity 1, one for activity 2, and one for that fragment. Here's how you enable that in your app. So if you can't read it, there's this parameter to Android binary called application module configs. And you give it a human-readable name, and you pass it a Buck rule, which is the root of that module. And Buck will do all the graph walking for you. And notice here, I didn't have to identify the fragment as a module on its own. Buck was able to determine that all by itself just by walking my dependency tree and seeing what was reachable from what. So that's it. Those are the ways that those are some of the challenges that we found and how we've overcome them, and the ways that we've exposed them via Buck's API. So let's recap. Here I've put side by side, from the moment that I've typed in the command and hit enter, the first build that I showed you, that completely non-incremental one. And on the other side, there's that hot swap build once again. And as you can see, one takes quite a bit more time than the other, and we knew this. But it's really apparent when you look at them side by side, and you look at not only the amount of time that I waited, but also the amount of work that I had to put in by interacting with the app, by tracking to make sure that, oh, as soon as I see it finish, all right, I'm going to go in and I'm going to reset the state. So I have to be paying attention. I put in some actual effort. I put in a little bit of mental effort. And over time, this really adds up. And this sort of drags by. I'm doing the same exact workflow in both of these scenarios, but one is both harder, more frustrating, and more time-consuming than the other. And so this is the type of thing that we work on, is trying to take things that fall into the category on the left and move them to things that fall into the category on the right, where not only have we removed time spent waiting, but we've also removed friction. If you're feeling really adventurous, we're releasing an alpha version of this, open source, to our GitHub, probably at the end of this conference. So Tuesday or maybe Wednesday, when you get home, you should see this land. You can enable it via the same ways that I've shown here. And I would love your feedback on this. If you maintain a state library of some sort or a view management library, please reach out to me. I'd love to know what it will take to support state refresh in your library. And if you try this and it breaks horribly, sorry, it's alpha. We're still working on testing it internally. But we wanted to make sure that we get it out there to you as quickly as possible. You can also email me or open a ticket on our GitHub. I look at every single one that goes through relating to this code. And so there's a myriad of ways that you can get involved. But if you have any questions right now, I'd love to take those at this time. Thank you. Yeah, and if you have questions, just come up to the mic so we can get it on record.
Hi, Josiah. Does the new Buck work well with Gradle data binding in Kotlin?
Well, so Buck is sort of mutually exclusive with Gradle unless you're using OKBuck to interop between them. As far as data binding goes, we don't explicitly support data binding. There's some work on a support library to sort of marry the two together, but that is not primetime ready at this time. And sorry, what was the third thing you asked about? Kotlin? We are starting to accept more Kotlin support into Buck right now. I think our amazing colleagues at Uber are driving a lot of that, and you'll see the story improve as we continue to start to use it at Facebook. We're just starting to use it for some secondary apps at Facebook. It's not in our main apps yet.
Thank you.
Absolutely. Any other questions? Go for it.
One question. So I see in the code you are using the reflection to load the class. So that one will solve the whole swap problem, but will that take longer time when you run it?
Yeah, absolutely. So to be clear, this is meant for your, thank you, that's a great question. To be clear, this is meant for debug mode only. This is meant to speed up your development. And so though I didn't necessarily show it here, I would expect to guard all of these with an if debug flag, and then you can use the explicit class reference for your production releases. I definitely don't recommend using this in to sideload code into your app when it's in the hands of your users. This is definitely just meant for you at your desk iterating to try and speed up your development cycle. So yeah, definitely strip this out of your release builds. But good question. It will slow things down just a little bit. Yeah, good question. So the question was, when you refactor a class and when you move it from one module to the other, and the reference has changed, how do you go back and you and find that that new class name, right? And you've referenced it in all these strings. So there's two answers to that, and the easy way out is that IntelliJ actually is pretty good at looking for strings that are fully qualified name references. And when you do a refactor, if IntelliJ has loaded your whole project, it is able to find those and replace them. The other answer is that we're looking at better APIs to expose. And so again, this is like really early days. This is the super simple, straightforward way. One method might be to use an annotation processor or a bytecode rewriter to take that the explicit class definition and rewrite it into a string at build time rather than forcing you as a developer to maintain it. But great question. All right. I'm happy to stick around and like chat with you individually. And I'll be here all day tomorrow, sitting over at the Facebook booth. Happy to chat there as well. Thank you so much and have a great rest of your day.